students, welcome to my fourth lecture in the dynamic stereochemistry series, and we will discuss today some stereochemical aspects of polar addition reaction to alkenes. As you can see here, we will be discussing two very important reactions. One is the bromination, as you can see, and another is the base hydroxylation. So let us start with the bromination reaction. As you can see here, we have the maleic acid and the fumaric acid. In the maleic acid, the two COH groups are cis to each other, and the fumaric acid, you have the two COH groups which is trans to each other. Now, addition of the bromine to this maleic acid can take place along the two phases, as you can see. These two phases are homotopic in nature, so bromine can give rise to the formation of a single achiral, say, bromonium intermediate, as you can see in this case. Now, this is a bromonium intermediate being generated due to bromination of the maleic acid. Now, when bromine adds actually anti to the bromonium ion intermediate, and as you can see here, the bromonium intermediate which is generated, this will undergo the attack with another Br minus, and with the addition of this Br minus and this opening up, this is opening up actually, and you will be finding here the one product which is having the S and the S configuration in this case. Now let me make it clear, this is the S configuration in this case. As you can see, you have read in the stereochemistry section how to find out the R as well as the S configurations. Now in the second portion, as we are having here the another intermediate to the maleic acid, now here the bromonium addition takes place, leading to the formation of actually to the bromonium intermediate, and then it is giving rise to this R and R configuration of the two carbon atoms which are achiral to each other. Now 1 and 2, as you can see, these are the enantiomers of each other, and the here point is that since it is the formation of the enantiomers being taking place with the RR as well as the SS, and these are equally probable to be formed. So, the bromination of the maleic acid results in the DL mixture as it is shown here with the dibromosuccinic acid, because we are getting the two enantiomers in this case. Now, after discussing the bromination of the fumaric maleic acid, let us discuss the bromination of the fumaric acid. As you can see here in this reaction, this is fumaric acid being coordinated to the bromine, giving rise to the bromonium intermediate along this phase. Now, when the bromonium intermediate addition this takes place, and here as you can see, it is giving rise to the anti-addition of the bromine, and with the anti-addition of bromine, you are getting this R and the S product. And here also you are getting here R and the S product is shown here. Now as you can see, it is actually a plane of symmetry being established here in this case. So let me just color it up. This is the plane of the symmetry being obtained in case of here. So this compound is optically inactive, and as you can see, this is the R as well as the S configuration over here. Now, considering the formation of the bromonium intermediate, in this case, the addition of the bromine just takes place, and the bromine gets opened up, and we get the R as well as the S product. So, in all the two cases, we are getting optically inactive compound, as you can see with the formation of the basically the optically inactive compound with the plane of symmetry having RS as well as SR. So the two compounds are identical, and we are getting the optically inactive product with the bromine addition of the fumaric acid. And we are getting the DL mixture as we studied in case of the maleic acid. Now we will be going into the next topic, which is the bis hydroxylation by the help of potassium permanganate. You all know that potassium permanganate actually forms a cyclic intermediate leading to the syn addition. In case of bromine addition, it was the anti-addition, and in case of the syn addition takes place in case of this potassium permanganate, as you can see here. Now let us study this. This is, as you all know, this is the maleic acid, and with the maleic acid you are getting this compound 3 on addition of this potassium permanganate, the bis hydroxylation being taking place, and this is the product being generated with the R and the S compound over here. So let me make it clear, when you are having the bis hydroxylation, the formation of the cyclic intermediate, then also it is giving rise to the 4, and when the cyclic intermediate formation occurs to the other phase, then it is giving rise to 3. Now 3 and 4 all are having, as you can see, this is RS and this is SR, and both are the meso compounds. So the tartaric acid which is formed is achiral, and it is named as the meso-tartaric acid in this case. Now, considering the other isomer, that is a fumaric acid, we will be learning how the bis hydroxylation does takes place in case of the fumaric acid, as you can see. Now, just look at this structure. This is actually giving rise to this cyclic intermediate to the fumaric acid by the addition of this potassium permanganate, and this is giving rise to, after hydrolysis, the compound 5 which is undergoing the bis hydroxylation. Now when the cyclic intermediate is formed into the another phase of the fumaric acid, then you are getting the R and the R product. Please mind that the 5 and the 6 are actually not meso compounds. These are actually optically active compounds, as you can see. And just look it into the reaction. This is the 5 and the 6 giving SS and the RR. So you may get a question that maleic acid gives rise to the meso-tartaric acid, but fumaric acid gives to the optically inactive compound. Why? Because the stereochemical aspects of such reaction dictate the reaction pathway. Now we will be moving into another reaction, which is the addition of HBr to the alkenes. You all know when we actually carry out this HBr addition to an alkene, then the addition can be either way. The addition can be anti or addition can be syn. As you can see here, these are the two enantiomers which are formed in the roughly equal amounts, where bromine and H are on the opposite sides, and here bromine and H are on the same side. So this is the addition of the HBr to the alkenes, giving rise to syn and anti. But when we discussed about bromine, we actually discussed that it undergoes the anti-addition. So when the addition of the bromine takes place to the anti-formation, then this is giving rise to the anti-addition, and you are getting only bromine added to the opposite position and not to the syn position. As you can see, the syn product is not being formed here, only the anti-product is being formed here. So the stereochemical aspects of this reaction is very important in this case. Now coming into the next reaction, which is the addition of H2 and palladium carbon in the presence of that is the reduction, it occurs only syn. In the previous case, in case of bromine, we were wondering it is occurring as the anti, but here it is occurring as syn. Now let us see the mechanism. This is the metal bed upon which actually the reduction takes place. Here, in case of this metal bed, you are having here H2 and this HH, and this is the alkene being shown here. With this formation, this is HH and CH2CH2, then the addition takes place and the alkane is formed. So the addition across the H2 is actually seen. So the seen product is formed here and the anti-product is not formed here. So let me ask you two questions. What will be the mechanism of, as you can see, these two reactions? Let us study this. This is an alkene undergoing the bromine addition. This is the cyclic compound undergoing the bromine addition. So let us just study the mechanism of these two reactions. Now, as you can see here, I will be going a bit further that in this compound, actually the bromine addition takes place to the anti, and as you can see here the anti-product has been shown. In case of this cyclic compound as well, this bromine is actually getting added and you are getting this Br and Br as the anti-product. So this is all about the mechanism of such reactions. Now, if someone asks you that what will be the products of addition of bromine to these alkenes. Now, let us see. So, in this case, the compound is undergoing bromine addition to give rise to the bromonium intermediate, and after addition of the water, there is the anti-addition being taking place, giving rise to the anti-product. In case of this cyclic compound, that is the bromine addition being taking place, here also, as you can see, the addition of bromine takes place and the water is attacking here and you are getting the anti-addition. So this is all about the stereochemical aspects of such reaction. Now, if you were given actually the cyclohexene structure, you all know that cyclohexene structure exists in the chair form. You have read that. In this case, the bromine additions gives rise to the bromonium intermediate and you are getting the addition to H2O and bromine. This is the formation of the trans-bromohydrine. So here also the stereochemical aspects are much important. Now, in the next series of reaction, I know this is a very hazy diagram over here, but I will try to explain it. I have given you an overview of all the reactions of the olefins. As you can see in the middle, this is the olefin. With the OSO4, you are getting the B's hydroxylation. With hydrohalogenation, you are getting this X and H being formed. With the halogenation, the 2X are added. And with the Cl2 addition and then followed by water addition, we have seen just now that in case of X and OH, the trans addition takes place. Now, if you add the CH2I2 in presence of zinc and ether, you are going to have the ether addition in case of this, the carbene addition in case of the olefin. In case of HgOSeOl2, you all know that is oxymercuration reaction and giving rise to again the OH, and with the hydroboration we are also having the formation of the H and OH, the addition, and by the help of H2O2 and the peroxy acids you are going to have the epoxide addition. So this will be much more important for you to remember when you are going for any competitive exam. Now this is the last example which is showing the electrophilic ring opening reaction. Here this is an epoxide, and with the epoxide the water addition takes place and this is the anti. And in case of the nucleophile in the aqueous medium, you are having the addition of OH minus. It is opened up and you are having the formation of trans diol. So in this lecture, we have discussed how we can study the stereochemical aspects of different additions, that is basically the cis hydroxylation and bromine addition to the olefins, that is the alkene derivative. In the next lecture, we will also study some other aspects of stereochemical aspects of different organic reaction. Till then, thank you.